So thank you for joining us today. As part of this four-part presentation, we're going to look at in situ remediation options for treating groundwater that has been contaminated with petroleum hydrocarbons or TPH. The term petroleum hydrocarbons or TPH is going to be an encompassing term that will also include PAHs, so polyaromatic hydrocarbons, as well as BTEX compounds and fuel oxygenates. So if you're looking at a site that is, say, a former gasworks site or a former petrol filling station site, or even just a site where there was an underground diesel storage tank, the different technologies that I'm going to present today may be applicable for you and that particular site. So this presentation has been divided into four parts. Each of these parts are going to be about 20-ish minutes long. The first of these talks, we're going to look at the principles of integrated treatment design. So that is how you look at different remediation options that are out there and choose the right option for the point at which you want to remediate your site. So we're looking at integrating different technologies depending on the contaminant level of your site and also what your aspirational cleanup goal is. So that may be you are just looking to augment a pump and treat system, or it might be that you are going to take a site where you've got three-phase contamination, augment a pump and treat system to recover that contaminant mass, and then once that treatment method becomes less efficient, you then start looking at other treatment options. So the first of these talks will be looking at enhanced desorption, essentially augmenting and improving the efficiency of pump and treat systems. The second of these talks will be reviewing a technology called REGENOX. REGENOX as a technology is probably used every working day across the UK, Ireland and Scandinavia. It's used on a wide range of sites, not only to remediate petroleum hydrocarbons, but also chlorinated solvents. And REGENOX works on the principles of chemical oxidation. So as part of that second talk, we'll look at this technology REGENOX and the principles behind chemical oxidation. The third of these talks, we will look at a technology called ORC, that stands for oxygen releasing compound, which enhances the rate of natural attenuation of petroleum hydrocarbons in situ. And then finally, we will look at absorption and bioremediation, utilizing one of our newer technologies, Petrofix. Petrofix is a liquid activated carbon that absorbs dissolved phase contaminant mass and then kickstarts the anaerobic biodegradation of petroleum hydrocarbons in situ. So we'll be covering things like this, where we can take a skim of free phase product, inject a technology called PetroCleanse into the ground, and then afterwards from that same well, you will see an increase in dissolved phase levels that can then be recovered using a pump and treat system. And then finally, we will look at how Petrofix, after a single injection, can yield a rapid reduction in contaminant mass, and that reduction will stay low for well over 1 year. So this shows you 12 months worth of treatment, where after a single injection, we've seen a 95% reduction in contaminant mass. It's also worth mentioning that during all of these talks, we will be covering different case studies, so real world examples of how these technologies have been applied and the results that you can expect to see. Before we get to the technology though, I just want to talk a little bit about integrated remediation treatment strategies. Sometimes these are referred to treatment trains, where you use different technologies at different points throughout your remediation program to maintain treatment efficiency. And this is something that is crucial for petroleum hydrocarbon sites, particularly if you are dealing with a site where you have very high levels of free phase contamination. So meters, and I've seen this, meters of free phase, measurable oil sat on top of the water, and you have a cleanup goal that is very stringent. This is likely because you have a very sensitive receptor nearby. Perhaps there is a drinking water well on site. So you need to clean up the groundwater to very strict criteria. So in order to do that, you need to change the treatment methodology, the technology that you're using to remediate that groundwater in situ. And when I think about petroleum hydrocarbon sites, conceptually, this is broadly what I see in terms of a graph. So if you think you have contaminant concentrations running along the bottom here. So over here, you've got sites where you have meters of free phase product. And then over here, you've got low dissolved phase concentrations. And then you have treatment efficiency. And then you have broadly what are the three types of remediation technologies that you could deploy. Is it going to be a physical technology? So when I say physical, I mean something like a pump and treat system or even a straight excavation. Is it going to be chemical? So the use of, say, chemical oxidation or a liquid activated carbon to absorb contaminant mass and degrade it, or biological. So enhancing the microflora that are already in the subsurface, the bacteria that are already in the subsurface, to break down any residual dissolved phase contamination in situ. Now, each of these technology types have their place, particularly on sites where you'll have high mass and your remediation targets are very stringent. You are going to have to reach for different technologies to maintain good treatment efficiency. So if we take, for example, a pump and treat system, and this is going to be the focus of this talk today, when you deploy a physical treatment system and you start it running, initially the efficiency is very good. You see great recovery rates of product, but as concentrations start to drop, that recovery rate will begin to reach an asymptote. So your recovery rate of free phase product will start to drop off, and eventually that system will no longer be efficient, will no longer be viable, will likely be doing very little to remediate the site. It's when that system starts to reach these asymptotic recovery conditions that we can look at augmenting it to improve the efficiency of that pump and treat system using a technology called PetroCleanse, which is this enhancing desorption agent. Next is technologies like REGENESIS, so these in situ chemical oxidants that can be used to address high dissolved phase levels of contaminant mass in situ through this process of chemical oxidation, so oxidizing that contaminant. Now, we would reach for this as a technology, REGENESIS, or another one that we have called Sulfox that falls outside of the full part talk that we're going to cover today, on sites where you have somewhere between 15 to 50 milligrams per liter TPH. So you may have dissolved phase concentrations that would suggest that you have free phase there, but you're not measuring it on the groundwater. The reason why we wouldn't go any lower than, say, 15 to 10-ish milligrams per liter is because chemical oxidation as a process relies on contact. The oxidant and the contaminant need to make contact with each other in order for that chemical oxidation reaction to occur. So as those concentrations drop, the probability of that contact occurring, of that exchange of electrons occurring, starts to drop off as well. So that's why typically at about 10 milligrams per liter, 15 milligrams per liter TPH, we wouldn't reach for chemox as a solution. Equally, if you've got lots of free phase contamination, you could absolutely chemically oxidize it. It's just that the efficiency of it doing that is going to be very low. It's going to be very expensive. So the most appropriate thing for you to do is to pump out that contamination. I should say, whilst I'm talking about this, talking about 50 milligrams per liter TPH, that I'm using an example where you're dealing with, say, a mixed diesel and gasoline plume. If we were looking at, say, a pure coal tar or a kerosene plume, these numbers wouldn't quite stack up. We'd have to use a slightly different example. It's to do with the solubility and bioavailability of that particular type of petroleum hydrocarbon. So this is broadly the examples that I'm going to be talking around when I say TPH in these concentrations, mixed diesel gasoline plume. And then finally, where you have concentrations of less than 10 milligrams per liter TPH, where you have to get down to concentrations below this, we would recommend utilizing biological remediation or bioremediation using a technology called ORC. So that's an oxygen releasing compound to add oxygen to the subsurface, to add electron acceptors to the subsurface, to create an environment where you grow a large microbial consortia in the aquifer so that you then break down contamination in situ. So broadly, this is what this four-part discussion is going to cover is enhanced desorption using PetroCleanse. Then we're going to look at in situ chemical oxidation using REGENOX. Finally, we'll look at ORC advanced, so bioremediation. And then here we have a newer technology called Petrofix that sits somewhere in between the two, that can kickstart the anaerobic biological degradation of petroleum hydrocarbons in situ and also absorb a significant amount of that contaminant mass as well. When you choose Petrofix, it's going to be as down to contaminant concentrations and broadly your conceptual site model, but also what your cleanup criteria is and how quickly you want that site cleaned up as well. Each of these have their advantages and disadvantages, and we will cover this as part of this four-part talk. What I'm hoping to do is to walk you through what you can do in the source area, so combination chemical and biological treatment, what you can do in the core of the plume. So it might be utilizing injections of REGENOX and ORC to reduce contaminant mass just down gradient of your source area. And then finally, enhanced biological treatment, which you can utilize on the distal end of the plume or even along your site boundary. So injecting things like REGENOX and Petrofix perpendicular to groundwater flow to mitigate against off-site migration of contamination, either to contain a particular liability on site or protect a sensitive receptor. So the first technology that we're going to talk about then is PetroCleanse, this enhancing desorption agent. For sites that we as REGENESIS can't help you with, this is probably a pretty good place to start. So if you have a site where you have meters of free phase contamination, a significant amount of oily water emulsion, and then your groundwater beneath there, so you can see that's in a baler. For those of you that may not know, balers are about 1 meter long. These are sites that we unfortunately can't help you with. Instead, you would, and it is what I would recommend that you do, is deploy some kind of physical treatment system. So in this case, a pump and treat system to recover as much of that free phase contaminant mass, that LNAPL, as possible. Pump and treat systems, though, is that they have a limited window at which they are efficient. So you initially deploy this system, you're getting good recovery rates of petroleum hydrocarbons, but quickly that recovery starts to reach an asymptote. So concentrations in the groundwater start to flatten out. Now, this is down to where that contaminant mass is in your subsurface. So you have absorbed mass, so contamination that is stuck onto the soil, and then you have contamination that is in your groundwater that's mobile. So initially, you recover that mass that's in the groundwater, and then you reduce that contaminant mass in the groundwater. Concentrations start to drop. As you reduce those concentrations in the groundwater, you have created a concentration gradient. And Flick's law says that you get desorption. So you have high concentrations on your soil, low in the groundwater. And it's that progressive desorption that has caused your system to reach asymptotic conditions and will prevent you from hitting your cleanup standard. What this means is that pump and treat systems can often run on for a very long time. So I've seen some where they've been running for 10, 15 years under these asymptotic conditions, not really getting anywhere. And secondly, they cost a lot of money to run. These things need fuel, these things need maintaining, there's operation and maintenance costs for these systems. So these are things that we need to factor in when choosing what kind of cleanup you're going to deploy on your site. Something else that's really important, and it's particularly important to us as REGENESIS, is to understand how the contamination in the subsurface is behaving so that we can target any treatment that we're going to deploy on the site accordingly. This is quite a useful visual. This is a sand tank experiment that was done at the University of Birmingham. You can see here that they filled it about 2/3 full with water, And then what they've done is released a petroleum hydrocarbon into the top of this sand tank. So you can see that it percolates down, hits the top of the groundwater, spreads out, uh, it spreads out across the top of that water, and then sits there. The thing is, though, we know as remediation practitioners that groundwater isn't static. It moves up and down, either with the seasons or due to tidal influence. And as it moves up and down, it creates this smear zone. And it's this smear zone that's also a it's this smear zone that is also a secondary source of contamination, and an important secondary source of contamination that we need to account for and often need to target using our technologies. It's also something to think about when you're designing pump and treat systems. You don't want to draw down your groundwater too much that you leave most of your contaminant mass in the vadose zone, and that when you turn that system off and groundwater conditions rebound, that you then see an upkick in contaminant concentrations due to that smear zone now being saturated. So overall, with pump and treat systems, the cost of contaminant removed over time will start to go up exponentially. And it's in this crossover point, in that inflection point, that we can start looking at augmenting that system utilizing a technology called PetroCleanse, this enhancing desorption agent. PetroCleanse as a technology is a two-part product. It's one part bicarbonate-based chemical oxidant, and then the second part is this PetroCleanse activator. Not to jump ahead too much as part of this four-part series, but if you have used Regenox on a site before, then you will absolutely be able to handle and apply Petrofix on a site. On the site, the mixing and application of this technology is very similar to Regenox. How PetroCleanse works is it temporarily raises the pH of the groundwater to about pH 11. So it reduces the charge and then therefore desorbs that contaminant mass from the soil. Once that contamination is then in the groundwater, it is partially chemically oxidized to form polar molecules. So one half of that molecule wants to be in the groundwater, and then the other half wants to be on the soil. But because you've raised the charge of because you've raised the pH of the groundwater, reduced the charge onto the soil, it can't do that. So these polar molecules bunch together to form surfactants, and these surfactants can then be recovered using a pump and treat system. And that's broadly how PetroCleanse works. What I will say is that as a technology, that rise in pH is critical, and it is also temporary. What we find is that after about 2 weeks, the pH of the aquifer will start to drop. It will get the pH will be buffered out by the soil, and it will return back to neutral conditions. So when you inject Petrofix into the subsurface, we always say to you, try and, if you can, monitor it daily. If not, twice a week or once a week as a minimum, just to keep an eye on that pH. Because if that pH drops and you haven't turned your system back on, or if you haven't recovered the petroleum hydrocarbons, then you could risk them being resorbed back onto the aquifer. So broadly, how this technology works, I'm just going to take you through this animation quickly. As I say, where you have sites like this, where you have significant amounts of free phase or LNAPL sat on top of the groundwater table, we would recommend that you deploy a pump and treat system. So in this example, and it's crucial for PetroCleanse, this is a total fluids recovery system. So here they're recovering contaminated water and free phase petroleum hydrocarbons or oil. Above that, you have this smear zone, so you have a large proportion of your contaminant mass in your vadose zone, your unsaturated zone, and you're getting progressive desorption from soils into the groundwater as you've created that concentration gradient as you've recovered the mass that's in the groundwater. This is how the asymptotic conditions are reached. So after you've been pumping, you have a low amount of recoverable mass both in your groundwater and free phase, but a significant proportion of that mass is in your soils. So you apply the PetroCleanse, you raise the pH, reduce the charge, and then partially chemically oxidize the petroleum hydrocarbons in situ so that you can recover as much contamination as possible. So as part of your treatment, you turn your system off, and then most PetroCleanse sites are done this way. You drop a packer down the well, you straddle the smear zone, so you inject typically across the top meter to top 1.5 meters uh, of your impacted groundwater and vadose zone. You leave it for 1 to 2 weeks for that desorption to occur, and then you drop down your pump and treat system. You drop down your pumps and switch the system back on. Crucially, that system has to be a total fluids recovery system, because we are looking at increasing not only free phase contamination, but also dissolved phase as well. Typically with PetroCleanse, we would recommend 3 applications. It could be 2.5, it could be 3.5, but typically 3 applications where you get 3 progressively smaller desorption events, where you've exhausted that contaminant mass, removed as much of it as possible from the soils, that can ensure that when you turn that system off, you're not seeing any rebound in contamination afterwards. So it's a good way of ensuring that you're not going to see any rebound in contaminant mass once that system has been switched off, because it can be really quite expensive if during the validation phase concentrations start to rise again, and you then have to redeploy that system to deal with that rebound. Broadly, this is what we're doing. Before you have PetroCleanse, you have a system where you have a low amount of recoverable mass, low dissolved phase concentrations, but most of it bound to your soil. You have that same contaminant mass after PetroCleanse has been injected, but a much greater proportion can be recovered using a pump and treat system. So I'm going to walk you through a case study now. This is a fairly typical PetroCleanse site. This is a site in East London in Woolwich. The backstory to this is that it was a former 1930s office building that was being converted into a series of flats, a series of apartments. The developer had done a due diligence exercise, and they had discovered that they had a free phase plume covering about 100 square meters across their yard area. And the source of this contamination was thought to be an above ground storage tank. So this bit here. Due to the different site constraints, they weren't able to do any excavation, and they also weren't able to have a pump and treat system sitting on a site for a long time. This was due to the fact that the site was midway through being refitted, repurposed. So there was lots of other contractors on site, so there just really wasn't a lot of room to play with. The remediation goals here, because we were in East London, the site wasn't particularly sensitive, was to remove free product down to 10 mil. But this had to be done quickly. So there was some significant commercial pressures on this site as well. So what we recommended that they do is install about 15 injection and recovery wells across the treatment area to facilitate injections of PetroCleanse and then subsequent recovery of the desorbed mass using a vacuum tanker. Now, what was interesting on this site was that we'd recommended 3 total injection campaigns, and these 3 total injection campaigns were spaced 1 to 2 weeks apart, and they kept an eye on the pH during that time. But what was interesting, and it's often the case with a lot of PetroCleanse sites, is that a lot of science has gone into the development of the technology, but when you deploy it on a site, it is a little bit reactive. And this is a really good example of what I mean by that. So initially we had recommended that PetroCleanse should be injected across all of these injection wells to cover this 100 square meter area. The problem though was, or rather the positive thing was, that after that first injection, what we found was that in this green area, we didn't see too much desorption. It indicated to us that there wasn't a lot of absorbed mass in the majority of this area. And subsequently there wasn't much free phase product to recover. What we did see, though, was a significant amount of desorption and rebound post-injection in this red area here. And then in this orange area, we kind of saw it perform as we would expect. So you saw some significant rebound in contaminant mass. So what this meant was that for the second and then third injection rounds of PetroCleanse, that we could concentrate that in the area where you had most of this sorbed mass. Ultimately, what this meant was that the client cleaned their site up much faster because we were able to be quite targeted with this. Really, those subsequent desorption events helped us map where the smear zone was, helped us map where most of that sorbed phase contamination was. And it also saved them money because ultimately they needed less product from us and they had less abstraction events or lower volume abstraction events booked in. In terms of how these abstraction and injection wells were constructed, these were down well injections. Broadly, what we recommend for injection wells is that you have a minimum of 1 meter of cement, 0 to say 1 meters below groundwater level. The reason for that is we are going to be injecting these technologies under pressure. This is true of all of the technologies that I'll be talking about. And this cement seal ensures that we maintain that integrity of the well, and it mitigates against the risk of the reagent daylighting. And daylighting is a term we use to mean that it erupts to the surface because it is flowing between the standpipe and the well construction rather than out into the subsurface. So this is your typical construction. Other than that, it's pretty similar to your standard monitoring well, to be honest with you. And here we used a down well injection packer. This is what the works look like on site. We were using our in-house injection crew to do this. All the mixing and application works were quite literally done out the back of the van. So our footprint on the site was very small. And these are the results that we were seeing. So this is your just visual indication that we're seeing an uptick in free phase contamination, but also a significant amount of oily water emulsion that we can then recover using a vacuum tanker system. In terms of results, so this is measurable free phase across all 15 abstraction and monitoring wells, just stacked one on top of the other. So you can see here that we had just over 4 meters of free phase if you were to add all of that up across that 100 square meter area. So not an insignificant amount of contamination, to be honest with you. We did 3 PetroCleanse injections followed by 3 abstraction phases. And what you can see is that peak in contaminant mass. You can see concentrations drop off, and then once that last abstraction event had been completed, there was a further here up to 4 months of monitoring where you saw no rebound there afterwards. And crucially, the site itself was signed off based on these results. In terms of the cost, the total cost of the application and the provision of PetroCleanse was around £30,000. That doesn't include for the installation of wells or the disposal of recovered mass. That was covered by the developer. But that gives you a flavour for how much this sort of treatment would cost. So that's enhanced desorption. It's often the first tool that we reach for sites where you have significantly high levels of contaminant mass. As part of the next talk, we'll be looking at in situ chemical oxidation. So where the use of augmented recovery using something like PetroCleanse, the efficiency of that has started to drop off. And then we're looking to pick that up using REGENESIS, so this in situ chemical oxidant that is used every working day across the UK and Scandinavia to address hydrocarbon plumes in situ. So thank you for that. I hope that you'll join me for the second part of this talk.